Hi, this is Jason Kendall. Welcome to the next in my introductory astronomy lectures. This time, we're finally getting to the most massive, compact, and bizarre objects in the universe, black holes. Black holes are the final triumph of gravity over matter. They are the end states of the cosmos and the horizons into nothingness. Let's take a closer look at exactly what these things are. First, we're going to learn about the history behind black holes. Back in 1783, scientist and clergyman John Michell carefully studied Isaac Newton's ideas on the nature of gravity. He was the first person to consider the idea of something like a black hole. He took seriously Newton's corpuscular theory of light. That was the idea that light was composed of a stream of particles that traced rays from some source. I described this idea in much greater detail in my video series on the history of science. Mitchell combined this with Newton's theory of gravity and imagined an object he called a dark star. In the November 1783 Annals of the Royal Society of London, he stated, "If there should really exist in nature any bodies whose density is not less than that of the Sun, and whose diameters are more than 500 times the diameter of the Sun, since their light could not arrive at us, or if there should exist any bodies of a somewhat smaller size, which are not naturally luminous, of the existence of bodies under either of these circumstances, we would have no information from sight." Here's Mitchell's argument. If light is made of particles, then to fly away from the surface of something, such as the Earth or Sun, it has to have been imparted with some kinetic energy. If the particle attempts to climb up out of a gravitational field with less energy than which it's needed to escape, then the particle must fall back down. Since the Sun is the center of the solar system, it's quite massive. Clearly, corpuscles of light somehow have enough energy to accomplish that today and in 1783 from the surface of the Sun. The actual gravitational force on a particle flying away from the surface depends on the mass and size contained under that surface. Mitchell asked, what would the mass of the Sun have to be such that its escape speed exceeded the speed of light? In 1783, they had a pretty good idea about what the speed of light was, and with Mitchell's numbers, if you kept the Sun's density the same, but made the Sun 500 times physically larger, then light could not exit from the Sun. In Mitchell's words from the paper, all light from such a body would be made to return to it by its own proper gravity. Thus, Mitchell termed such theoretical objects dark stars. For those playing along at home, with better numbers for the Sun's mass and size and the speed of light, it works out to be about 150 times the size, or 70% of an astronomical unit. In 1796, independent of Mitchell, Pierre-Simon de Laplace, one of the most famous mathematicians of the 18th century, and even in all history, discovered that there really could be stars whose gravitational field could be strong enough that the escape speed would be the speed of light. Where Mitchell's arguments were mostly philosophical in nature, Laplace developed his line of reasoning with mathematical rigor. There is some debate about whether or not Laplace knew of Mitchell's arguments, given the political troubles between France and England at the time. Even still, Newton's conception on how gravity operates really did create a ripe new world ready for learning. It took until Einstein's reformulation of gravity into a geometrical construct before any major advancements occurred. Carl Schwarzschild produced the first exact solution to the Einstein field equations of general relativity. He set them down in a letter to Einstein on the 22nd of December in 1915. He wrote this work while serving in World War I, stationed on the Russian front. Schwarzschild concluded the letter by writing, "As you can see, the war has treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." The field equations at the top describe the relationship between the curvature of spacetime and the matter and energy embedded in that spacetime. His solution below was for spacetime surrounding a static, non-rotating, spherically symmetric matter distribution with nothing else in the universe. We'll look at this in greater detail later. In 1916, Einstein wrote to Schwarzschild about this result. "I have read your paper with the utmost interest, and I had not expected that one could formulate the exact solution of the problem in such a simple way. I liked very much your mathematical treatment of the subject, and next Thursday I shall present the work to the Academy with a few words of explanation." Schwarzschild died the next year of a genetic disease that developed while serving in the German army. Who knows what other contributions he could have made had he been able to live a much longer life. Then, about 20 years later, in 1939, J. Robert Oppenheimer and his graduate student Hartland Schneider described what would happen to a star that had exhausted all forms of nuclear fusion and exceeded the limit of neutron degeneracy pressure. With nothing to hold it up, it would collapse down to an infinite singularity, a black hole. And it is this paper where the term black hole comes from. Oppenheimer himself, just earlier that year, with a couple of others, had figured out how neutron degeneracy could support an ultramassive compact object, which he termed a neutron star. Oppenheimer and Snyder then wondered what would happen if that broke down, and concluded that nothing could support the mass of the compact object. They found that this object would freefall all the way to a singularity with nothing left in existence below it or inside it. It would be a true singularity. Let's look a bit closer at Oppenheimer and Snyder's reasoning, starting with the properties of white dwarfs. White dwarfs are extraordinarily dense objects possessing a mass approximately equivalent to that of the Sun, but a volume of a typical white dwarf is comparable to that of the Earth. The gravitational stability of a white dwarf is maintained through the pressure of degenerate electron gas, rather than through a more familiar gaseous states, and certainly not a liquid or solid state. The gaseous nature of white dwarfs is more akin to a solid, but only in a colloquial sort of way. A degenerate electron gas is characterized by the electrons occupying the lowest possible energy states, which prevents any further compression of the gas, even if there is some large addition of mass to the star. As we saw in my video on white dwarfs, the odd thing about a degenerate gas is that if additional mass is introduced into a white dwarf, its physical size will decrease. In other words, its radius shrinks the more massive it gets. Because of this, there is a maximum mass for white dwarfs. The maximum mass threshold for a degenerate electron gas is 1.44 solar masses. This is known as the Chandrasekhar limit. It comes about because, as the allowed position momentum states for the electrons get filled up, the only available momentum states are those with speeds rapidly approaching the speed of light. Since no physical object can go faster than light, or even at the speed of light, this gives a firm upper limit to the allowed mass of white dwarfs. The implications of this limit are profound because they dictate all the evolutionary pathways of all stellar remnants. The Chandrasekhar limit is not something that is easily breached. However, if the conditions are right, electron degeneracy can be bypassed and superseded by another such pressure. Much more massive stars than the Sun are capable of producing a Type II supernova. If such a star has, say, a pre-supernova mass exceeding approximately 18 solar masses, it would result in a supernova with a core mass larger than about 2.5 or 3 solar masses. In such instances, electron degeneracy pressure is bypassed by the creation of a neutron-rich core during the supernova. This leads to neutron degeneracy, which is a similar process, but the size scales are much smaller. A 1.5 solar mass neutron star is about 10 kilometers across, or roughly the size of a big city like Manhattan Island. Just like electron degeneracy, if you add mass to a neutron star, it shrinks. The maximum mass of neutron stars is not really well known because the nature of matter under such conditions is also not really well known. In any event, if too much stuff accumulates on a neutron star, then neutron degeneracy pressure can fail to counteract the immense gravitational force acting on this core. The range for viable neutron stars lies between about 1.5 or 2 or 3 solar masses. Therefore, if the core's mass surpasses approximately 3 solar masses, it will inevitably undergo collapse during the supernova. The work of Oppenheimer and Snyder established that there exists no known force within the framework of physics that can halt this collapse. In fact, general relativity indicates that pressure itself contributes to the energy density, and as the pressure increases, which further accelerates the collapse. Therefore, any mass exceeding about 2.5 or 3 solar masses confined in a radius of about 10 kilometers lacks any structural support, and the core is forced to collapse into a singularity. And this results in the formation of a black hole. Black holes are not merely voids, but are rather entities with distinct characteristics. The white ring in this image can be conceptualized as some sort of surface with unique properties. Now let's see what these are. The first property we'll look at is that of Mitchell's dark star and escape speed. To understand the concept of escape speed, we must revisit its definition and implications. Traced back to 1783, the notion posits that if an object reaches escape speed, it can overcome gravitational forces and leave a celestial body such as the Earth. This speed is crucial because if an object achieves it, it will have escaped the gravitational influence and will not return without a new force being acted upon it to bring it back down. We can express this idea in the framework of conservation of energy. The classical kinetic energy of an object is expressed by the formula 1/2 mv squared, where m is the mass of the object in motion and v is its velocity relative to some other object. In this case, the surface of the Earth or Sun or star or black hole. To determine the escape speed, we equate the kinetic energy to the Newtonian gravitational potential energy, here represented as gmm/r, where g is the gravitational constant, big M denotes the mass of the celestial body being escaped from, and big R being the distance from the center of mass of the celestial body. We derive the escape speed by solving for v. This is the minimum velocity required to exceed its gravitational potential energy in this two-body system. For example, if we choose a rocket leaving the Earth, we substitute the Earth's mass and radius to yield an escape speed of approximately 11 kilometers per second. This is very fast. For context, elite athletes may complete a 10-kilometer road race in 20 to 25 minutes. On the faster side of things, Voyager 1, which is the farthest object ever created by humans, is currently zipping away at 17 kilometers per second. And there are no rockets on Voyager 1 pushing it along. That's its coasting speed. It would travel from New York City to Los Angeles in less than 4 minutes, or from New York to London in less than 5.5 minutes. To riff on Mitchell and Laplace's ideas, let's see what happens if you shrink the Earth. Right now, if your rocket travels upward at only 10 kilometers per second, you will ascend to a great height, but you will eventually fall back down. Any speed slower than 11 kilometers per second will fall back down eventually. But if you go faster than 11 kilometers per second, you will escape the Earth's gravitational pull. Now, let's shrink the Earth while keeping its mass the same. We'll compress it, say, 100 times smaller, to about 65 kilometers in diameter. Now the escape speed would be 110 kilometers per second because it's related to the square root of the radius. But if we want the escape speed to be 300,000 kilometers per second, the speed of light, we would need to shrink the Earth to about 1/3 of an inch or a few millimeters, all while keeping the mass of the Earth the same. This is incredibly small, smaller than a centimeter or about the width of your pinky nail. So if you could compress the entire Earth, which normally measures about 12,000 kilometers across, into the size smaller than your pinky nail, the escape speed from the surface would equal the speed of light. This is an extraordinary compression ratio, and what could achieve this? Only a supernova can cause such dramatic changes in size and density. Mitchell's dark star is exactly this kind of object, where the escape speed is equal to the speed of light. A black hole is an incredibly dense region in space where gravity is so strong that nothing, not even light, can escape. This phenomenon occurs when a large amount of mass is concentrated in a small volume, creating intense gravitational forces, as I've described previously. As matter approaches a black hole, it undergoes spaghettification due to tidal forces, which I'll talk about in a bit. Importantly, since nothing can hold up or support the matter so compressed, it must, of necessity, collapse down to a true singularity. The term black hole was popularized by physicist John Archibald Wheeler in the 1960s, but was really coined by physicist Robert Dicke, who in the early 1960s reportedly compared the phenomenon to the Black Hole of Calcutta, a notorious prison where people entered but never left alive. The name reflects the object's nature: black because it emits no light and is visible against the backdrop of space, and hole because nothing that crosses the event horizon can escape. The event horizon, I'll talk about in a little bit, is the boundary surrounding a black hole. This combination of characteristics makes black holes among the most fascinating and mysterious objects in the universe, and the subject of a lot of childhood dreams, sci-fi novels and shows, and wild speculation. It's why, when I give public talks in, say, New York on a completely different topic, like Pluto or the Big Bang, I almost always have somebody ask me something about black holes. To that end, the appearance of singularities in general relativity really signals the breakdown, or more specifically, the boundaries of applicability of the theory of general relativity. It generally is understood that quantum effects should describe the environment just above and inside the surface of a black hole due to the extremely high density and therefore particle interactions. However, to date, it has not been possible to combine quantum and gravitational theories into a single quantum gravity theory, although there exist a lot of attempts. Importantly, it is generally expected that such a theory will not feature any singularities. Just as important for your understanding, whatever this solution is, whenever it might occur, it won't be easily popularized on this or any other YouTube channel. It'll be a tour de force of physics and mathematics that'll have to be hand-waved really hard, basically into what I've just stated. Now let's dive into the concept of the Schwarzschild radius, which is critical for understanding black holes. This radius is derived from the Schwarzschild metric, the mathematical framework we saw previously. It is, of course, how we describe accurately the measurement of space and time around a spherically symmetric object. The Schwarzschild radius defines the size scale of the region in and around black holes. It also determines the size of the black hole itself. If any object or light ventures inside this boundary, it is guaranteed to fall into the singularity, regardless of the circumstances. The formula for the Schwarzschild radius is r sub s equals 2gm over c squared, where g is Newton's gravitational constant, c is the speed of light, and m is the mass of the object inside the Schwarzschild radius. This means you can take any mass, be it the mass of the Earth or a million solar masses, and it is this equation that determines that mass's Schwarzschild radius. The composition, type, and nature of the matter inside the radius doesn't affect the outcome. It's just the total enclosed mass. For instance, a black hole with a mass equivalent to that of the Sun has a Schwarzschild radius of approximately 3 kilometers, and in contrast, a white dwarf with the same mass has a radius about the same as the Earth, roughly about 6,000 kilometers. And a neutron star measures around 10 kilometers. Notably, the size of a black hole is only marginally smaller than that of a neutron star. Neutron stars are situated right at the threshold of being compressed within their own Schwarzschild radii, which makes them incredibly extreme states of matter, as I've explored in other lectures on neutron stars. Let's explore the relative sizes of black holes by making size comparisons. Here we have an image of the Sun taken in ultraviolet light, showcasing a beautiful solar prominence reaching out from its surface. For scale, the Earth is placed underneath the prominence, and it's important to remember that about 100 Earths could fit across the diameter of the Sun. So the Earth is really small compared to the Sun, about 1%. Now let's zoom in closer. As we do, we see the size of the Earth in relation to this prominence. And these features in the Sun's atmosphere are really common and amazing. Check out my videos on the Sun to learn more about them. Next, we zoom in on the Earth and on down to Florida, and we focus in on a specific area on the east coast of Florida, and we keep zooming in until we discover a black circle representing the size of a black hole that has the same mass as the Sun. This black hole would be incredibly small, roughly a few kilometers across, and this means if we could compress the entire mass of the Sun down to this size, the same size as Cape Canaveral, where the Apollo missions launched to the moon, we would have a black hole. A black hole of this size, of course, if it were placed right next to Cape Canaveral, would make the whole place undergo a huge number of tidal forces that would rip it all apart. Now let's introduce a new term, the event horizon. The Schwarzschild radius helps define what we mean by the event horizon, which surrounds the black hole's singularity. Any events occurring inside the event horizon, or within the Schwarzschild radius, are invisible to the outside universe. Light cannot escape from inside this area because it would need to travel faster than the speed of light to do so. Therefore, nothing that happens inside the Schwarzschild radius can be observed. And this is the essence of what we mean by a horizon. Horizons are boundaries that you cannot see beyond or around. For instance, because of the curvature of the Earth, there is a maximum distance that objects can be seen. If they're not very tall and are so far away that the curvature of the Earth arcs them below the horizon, you can't see them. They can't be known about, unless, of course, you go up in the air or use satellites or whatever. The event horizon is similar, but it is a horizon in space-time. The event horizon is a boundary beyond which we cannot observe or interact with anything for all future time. Once something crosses that event horizon, it can never escape. It is forever trapped within the black hole, and this would even be true of quantum gravity theories. Nothing escapes from a black hole. This is the fundamental nature of the event horizon defined by the Schwarzschild radius. It's important to note that the event horizon is often visualized as a black surface, but it isn't actually a physical surface. There is nothing actually present at the event horizon. Instead, it's simply the boundary from which light cannot escape and making it appear black. Inside this boundary lies the black hole's singularity, or whatever a quantum gravity theory might one day cook up. But because we cannot see anything beyond the event horizon, no events can be observed from within that area. The gravity right around black holes is incredibly intense, but there's an important detail that many people don't quite get. Let's consider a black hole with one solar mass. When you're close to its event horizon, which is about 3 kilometers in radius, things become really strange. However, if you're far away from the black hole, it still behaves as just a one solar mass object. For instance, if the Earth were orbiting 1 astronomical unit away from a 1 solar mass black hole, the only significant difference compared to our current situation would be the absence of sunlight and the copious presence of X-rays generated by infalling matter passing the event horizon. Nevertheless, we would still orbit that black hole in the same manner we now do orbit the Sun. Kepler's laws would still apply, Newton's version of gravity would be valid at this distance, and the Earth would not be sucked in by some cosmic vacuum cleaner principle or the Hollywood movie principle. However, it's different when you're close to the event horizon. When your orbit is less than about 3 times the Schwarzschild radius, stable orbits no longer exist. The gravitational potential in the strong field of a hypercompact object is not at all the same as the familiar Newtonian 1 over r potential. However, once you're within 3 times that Schwarzschild radius, nothing can maintain a stable orbit. Tiny changes in orbital parameters will radically change the orbital trajectory close in, either plunging you in, flinging you out, or sending you on a wild, non-elliptical winding orbit that would make a carnival tilt-a-whirl look tame. 3 Schwarzschild radii marks the radius of the innermost stable orbit. Outside this radius, circular orbits are stable, whereas within it, circular orbits are unstable. Therefore, if a black hole is accreting material from, say, a companion star, then the inner edge of the accretion disk probably lies at the innermost stable orbit. At that radius, gas peels off from the accretion disk orbiting the black hole and falls headlong straight into the black hole. Inside that 3 Schwarzschild radius boundary for matter orbits, we find that light's innermost stable orbit in a circle is at about a distance of 1.5 times the Schwarzschild radius. This distance above the event horizon is a special location, the photon sphere, where light rays can orbit in circular orbits around the black hole. This is the closest to the black hole where anything can remain in a circular orbit without needing constant orbital thrust. But photons don't have rockets, so photons can, in principle, get stuck in circular orbits at the photon sphere. In practice, though, the orbit is unstable, so photons do not concentrate there, and there would be nothing special to witness there if you were to fall through the photon sphere. So why do all these phenomena occur? In my lectures on general relativity, I went into great detail about the concept of the equivalence principle. The equivalence principle represents Einstein's profound insight into the nature of space and time. Essentially, it states that all physical laws remain the same regardless of how the laboratories in which they are measured are moving with respect to each other. For example, suppose you're standing in a windowless room on the surface of the Earth. Here, you'll experience the same physical laws as someone in a windowless rocket that is accelerating upwards with the same rate as the gravitational pull on the Earth. In other words, there's no way to distinguish between being in a room on the Earth's surface and being in a rocket accelerating upwards at 1g. Similarly, if you compare the experience of floating freely in space in a box and a similar box falling toward the Earth, you wouldn't notice any difference between the two scenarios. Einstein summed this latter situation up with the phrase, "all freely falling reference frames are identical." Of course, there are significant distinctions between these situations when viewed from the perspective of an outside observer. Of the bottom two depictions of the freely falling frames, one will run out of food or air, and the other will soon discover what concrete feels like. The one on the right, of course, will experience tidal effects, while the one on the left will not. But that's because the Earth's gravitational field is not strictly uniform. This radial infall will become important for extremely strong gravitational fields, but even then, the equivalence principle is valid, so long as you make the laboratory frames small enough and measure over short enough intervals to be able to ignore the tidal effects. Most importantly, it is this principle that underpins the geometric interpretation of spacetime. Within your laboratory, no matter where you put it, you will measure the same physical laws. Freely falling frames are all the same. Stationary frames in gravitational fields are the same as constantly accelerated frames. Of course, there would be rocket vibrations or birds chirping or what have you, but if you remove these and other particularities, which would differ from place to place, the underpinning principle will always apply. It is this principle that leads to some very intriguing implications for black holes. Let's further clarify the concept. The equivalence principle states that all physical laws, whether they pertain to quantum mechanics, electrodynamics, mechanics, or thermodynamics, are the same for all inertial observers, regardless of their state of motion. So whether you're in free fall, floating, standing still, or moving at a constant speed. And if you're experiencing a uniform gravitational field or a constant acceleration, there's no way to distinguish between these various scenarios using known physical laws. This is incredibly important because the classical general relativity, which describes gravity, indicates that gravity is a physical law quite unlike these other laws in that it reflects an interaction that underpins all these other laws. To put it differently, Newtonian gravity, represented by, say, F equals gmm over r squared, is then completely reinterpreted. Instead of seeing gravity as a force requiring the interchange of particles or collisions that impart momentum or some sort of gravitational charge, we can understand gravity as the modification and alteration of spacetime. In this view, we say that spacetime is curved, and that objects fall along the paths defined by that curvature. There is no force acting on them. They're simply following the lay of the land. So far, general relativity has withstood exceptionally rigorous testing, including remarkable experiments related to gravitational waves. These tests provide strong support for general relativity as the most accurate description of gravity. Presently, the predictions derived from general relativity are testable and have been consistently validated by numerous experimental results. Now for the fun stuff. What's it like to fall into a black hole? Let's imagine two astronauts, Jack and Jill. Jack is going to leap out of a perfectly good rocket and fall toward a black hole, while Jill will stay behind. Jack, thinking it might help him get a contract with an extreme sports channel, dons his spacesuit and enters a small pod. He has a blue laser, which he will use to send signals back to Jill. As Jack falls towards the black hole, he begins shooting the laser in pulses, 1 pulse per second, and Jill watches him from the rocket, observing his descent. From Jack's perspective, the ship proceeds into the distance as he flashes the blue laser once per second according to his watch. Soon, Jill starts to notice something unusual. The farther away Jack gets, the longer it takes for it to receive the next laser pulse. Each successive pulse arrives later and later. Furthermore, the wavelength of each pulse becomes longer, shifting towards the red end of the electromagnetic spectrum. Lastly, the pulses become fainter and lose intensity. As Jack continues to fall, all of these effects only increase in magnitude. Jack notices the outside world becoming increasingly bizarre. The stars around him appear to be wildly distorted as their proper motions accelerate to astonishing speeds. Looking down, he sees the black hole looming below him, filling his downward field of view. He also starts to see devastatingly bright flashes of light from infalling matter accelerated to great speeds, colliding with other matter surrounding the black hole. Gamma rays start to increase due to intermittent cosmic ray-like interactions in the area surrounding the black hole. While the hole is dark, the surrounding space is teeming with activity. He is very near the event horizon at this point. Meanwhile, Jill still witnesses Jack's laser flashes, but they are now spaced very far apart, only about, say, once an hour. As Jack gets closer to the hole, the laser flashes are redshifted so dramatically that Jill must adjust her receiver to an AM radio frequency just to perceive them. She no longer sees the flashes directly, perceiving them only as faint radio signals waning ever weaker. If Jack had started with a dim laser, Jill wouldn't have been able to see it at all. Finally, Jack reaches and passes through the event horizon. From Jill's perspective, before he crosses it, she sees one last pulse from the laser. All the pulses prior to his plunge across the boundary came months or even years apart. Jack's last pulse was extraordinarily faint. In order to see his last transmission, Jill deployed a massive radio antenna array because the wavelength of the pulse had been stretched to tens or even hundreds of kilometers. After this one last blip, she never sees another flash from Jack. Down near the hole, Jack is unaware of all this. For him, all the laws of physics remain the same, as indicated by the equivalence principle. As he falls, he continues to experience time at a regular pace, ticking away 1 second at a time. Tick, tick, tick. He is still theoretically able to shoot a blue laser, so long as the black hole's environment can be dealt with by his little space pod. As Jack neared and crossed the event horizon of this stellar mass black hole, he felt some pretty strong tidal forces. It was pretty uncomfortable, as his feet got ripped away from his ankles, which got ripped away from his knees, and so on. He was completely and rapidly shredded and pulled apart. This effect is so extreme that even molecules were pulled apart to their constituent atoms, which then get pulled apart onto their quarks. It's kind of bad for Jack. Jack would have fallen towards the hull happily, without incident, for some time after he stepped out from the spaceship when he left Jill behind. But in the last few seconds, as he drew near the few Schwarzschild radii from the hole, his world became quite unpleasant. Once he crossed the event horizon, or rather, what was left of him, which wasn't much, plunged into the singularity in a tiny fraction of a second. Jack's fate, from the moment he waved goodbye, was to be crushed to infinite density in the singularity at the center of a black hole. Since Jill was a party to this event, we may surmise that Jill's relationship with Jack was somewhat strained. Now let's take a look at some of the effects that Jack and Jill experienced, first focusing on gravitational redshift. Gravitational redshift occurs when a photon emerges from within a strong gravitational field. For example, let's say some light-emitting process is positioned at about 10 kilometers outside a 1 solar mass black hole. It emits first at visible wavelengths of light. That light will be redshifted to infrared after it travels approximately 100 kilometers away, and to radio wavelengths after it travels 10,000 kilometers. If the emission were X-ray light, which would originate in the inner rings of a black hole's accretion disk, such light would be redshifted down to ultraviolet and then to visible light by the time it travels 10,000 kilometers away. We again can define the redshift z to be the difference between the emitted and the observed wavelength of light compared to the wavelength at the moment of its emission. The equation at the bottom shows the wavelength we would observe if we were situated at a very large distance away from the black hole, where gravitational stretching of space-time is negligible. Our vantage point, 1,000 light-years away, would suffice. Lambda sub e is the wavelength at emission, and lambda sub lazy-8 is the far distant measurement. The big r sub e represents the radius from which the light was emitted, and the little r sub s denotes the Schwarzschild radius. For example, the H-alpha Balmerg transition comes from an excited neutral H atom at 656 nanometers. Let's imagine we were somehow able to identify that this transition had been redshifted by a black hole all the way to microwave wavelengths, observing that emission line at, say, 6.56 centimeters. The light from that hydrogen atom came then from approximately 0.03 millimeters above the event horizon. This was the final call of that atom before plunging into the hole. Atomic transitions are not really expected to be relevant at the event horizon. More likely are nuclear transitions, which would occur at X-ray wavelengths. So, let's say some nuclear transition rate occurs at, say, 50 picometers at the same tiny altitude above the event horizon. That would be redshifted down to about 500 nanometers, or visible wavelengths. The realistic amounts of large redshift, though, occur from light emitted from a range of distances, perhaps a few hundred Schwarzschild radii down to the innermost stable orbit of 3 Schwarzschild radii. This corresponds to the accretion disk found around black holes with companions or supermassive black holes in the centers of galaxies. So, let's take the 3 Schwarzschild radius as our typical value. An X-ray emitted from the inner edge of such an accretion disk will have a typical change in wavelength of about 1.22 times the original. Thus, an iron K line at 0.2 nanometers would be redshifted from that origination point to about 0.24 nanometers. This might not seem like a lot, but it is enough to measure. The other significant concept we find from this catastrophic interpersonal relationship is the observed gravitational time dilation. For example, Jack's clock consistently shows that time passes normally, 1 second at a time, and that's his metric for laser pulses he sends back to Jill. However, Jill observes and measures the intervals between the pulses of Jack's clock getting larger. This is a closely related phenomenon to the redshift. The redshift measures the interval of time between individual crests of the emitted light's waves, and the time dilation is a macroscopic view of that same event. Rather than individual wave crests, it is some big tick-tick-tick of some series of events. Thus, the time dilation is in some sense more obvious to Jill. The intervals are represented by delta t sub e and delta t sub lazy 8. They're related by the same equation as the redshift, which obviously arises from the definition of wave speeds. As a result of this time dilation, from Jill's perspective, Jack will never seem to cross the event horizon. This is because, as she measures it, his clock is slowing down more and more. If Jill could somehow view Jack and see the dim, redshifted light coming from him, she would perceive him as having stopped all movement, never actually crossing the event horizon. There would be a final image of him represented by a light reflecting off him. Perhaps he shone one directly on himself. Any light signal coming from Jack's location would be greatly redshifted. This was interestingly done in the sci-fi series Stargate, where the Gates planet collided with a black hole. The remote's team image was frozen. Also, the old anime classic Gunbuster featured a team coming out of a black hole's well to similar effect. This effect has been observed and measured in less extreme and nearer environments than black holes. The Hefele-Kating experiment used atomic clocks on airplanes, comparing them before and after their flights on an average commercial passenger liner. The clocks aboard the airplanes were slightly faster than the clocks on the ground, depending on the direction they flew. Closer to home, the global positioning system would not work at all unless this effect is taken into account. Closer than a geostationary orbit, lab experiments have shown to measure the effect over distances of about a meter or so. The Pound-Rebka experiment is the classic test of this in the form of a redshift, and researchers using the Hubble Space Telescope found it in the spectra of the white dwarf Sirius B. In the solar system, it was measured in the signals between the Viking Lander 1 on Mars in 1977. Basically, what I'm trying to tell you is this time dilation is a real thing. Again, r sub s is the Schwarzschild radius and r sub e is the emission radius for the signal. To make 1 second of Jack's into 10 seconds of Jill's, Jack would have to be about 30 meters above the event horizon of the solar mass black hole. It really was his last call back to her. Finally, we look at Jack's experience of spaghettification, which is the stretching and squeezing caused by the black hole's intense, non-uniform differential gravitational forces. It is non-uniform in the fact that gravity is directed radially inward towards the center of mass. For large objects like the Earth, Moon, and Sun, this is a subtle effect because up to a rather large area of the surface and up to some very large distances, the radially directed lines of gravitational force are roughly parallel. But once you have a big mass in a small enough region, the surface curvature of the object makes the radial lines of force diverge. It also means that the force of gravity between two nearby altitudes can be great. These combine to give very large tidal forces near a stellar mass black hole, and this will distort objects. Let's say we have 4 balls in a free fall toward a black hole. We see how the far one doesn't fall too much, but the near one does, and the other 2 start to converge in the middle. This is the essence of spaghettification. Normally, most materials' intermolecular and interatomic forces would keep the shape of the object. Under the extreme tidal stresses and strains near a small black hole, these bonds would not be enough to prevent the distortion. In Jack's case, as he gets closer to the event horizon, the difference in gravitational pull between his head and his feet becomes extreme. Soon, the force on his feet, which are closer to the hole, will be significantly stronger than the force on his head. Also, the convergence of the lines will force him to thin down, and his various parts simply cannot stay bound together. The outward keeping structure of his ribs would not be enough to prevent the inward strains. As a result, he would effectively be pulled into a long, thin shape, resembling a strand of spaghetti, hence the term spaghettification. Now, if Jack had fallen into a supermassive black hole, the physical size of the Schwarzschild radius would not lead to the effect above the event horizon, but would rapidly happen within it. For stellar mass black holes, though, it would happen above the event horizon. In either scenario, deep inside the event horizon, Jack would be squished to a point where he could be narrower than an atomic nucleus, and ultimately the matter that makes up his body could be compressed down to scales as small as the Planck length. Meanwhile, Jill, sitting in her spaceship 300,000 kilometers away, watches this calamity unfold. From her vantage point, she would observe Jack getting stretched and distorted before ultimately disappearing into the black hole. The sight can be unsettling, especially as she drops a beach ball to test the gravitational effects, only to see it shredded by the black hole's force. If Jack had seen the beach ball torn apart, it might have made him reconsider his decision to jump, or not. We're not exactly clear on Jack's motives in this little tale. Now let's see what Jack sees as he plunges into the black hole. Here, rather than dropping straight in, he spirals around the black hole, dropping ever closer as he does so. As Jack gets nearer, he eventually passes through the stable orbits where he could have orbited safely. Throughout his descent, the black hole remains directly below him. Eventually, Jack crosses the event horizon, continuing down to the singularity. At this point, he is at the center of the hole. It is interesting to note that even when reaching the very center, Jack continues to see stars above him while the black hole looms as a vast plain below. Basically, Jack never gets to see the singularity because all the light is headed towards the singularity and none is headed away from it. At the center of the black hole is the singularity, which is a place of infinite curvature, where space and time as you know them come to an end. And the geometrical intuition that would suggest that the center of the Schwarzschild black hole is a point. Well, that intuition is misleading. If Jack had a friend alongside him while he fell into this black hole at the same time, but at some different location, as in a different latitude and longitude with respect to the event horizon, they would not approach each other as they approach the singularity. Rather, the diverging tidal force channels of the parts of their body along inward radial directions. Far from Jack meeting his other doomed companion at the singularity, he would not even be able to put out his arms to touch her. The singularity is not a point. Rather, it is a three-dimensional spatial boundary where general relativity no longer works or applies. Some new physics, presumably quantum gravity in some form, must replace general relativity at these singularities. In addition to being a boundary in space and time, it's also a boundary of our knowledge. This simulation comes from Dr. Andrew Hamilton, a prominent black hole researcher at the University of Colorado. He has extensively studied mathematics of black holes and published numerous papers and creating some amazing simulations. And so I've included a link to his work, and I'll point out where you can find his materials on these websites. In addition to seeing Jill seeing Jack falling into the black hole, she's also struck by the sights around her. They didn't just plan their stunt in an isolated location. They planned it in an area that abounded with background stars. This gave both of them some amazing views of the background stars that were quite unexpected. Because general relativity states that spacetime is curved, the most important element of that statement is that straight lines through curved space appear to a distant observer to have been bent, warped, or shifted. From the observer's perspective, where you perceive that you are looking in a straight line over there, your intuition tells you that straight lines emanate from your eyes, from the source to the destination. However, this perception is incorrect or at least highly deceptive. The actual path of light from its emission to its reception is by definition in a straight line. Light only takes straight lines in its travels. Very technically, light parallel transports along a null geodesic and therefore takes the shortest possible path from the source to the destination. This parallel transport assures that the arrow pointing in the direction of light's travel does not change direction from one step to the next. Without a change in the orientation of light's direction of propagation, it is moving in a straight line. But then, why does everyone say that light's path is deflected, bent, or warped? This is because we have a cultural bias of being a distant observer, that we can see the background stars and with practically no curvature between us and them. The marauding black hole's gravitational well, caused by the curvature produced by the Schwarzschild metric, shows us an image of a distant object beyond the black hole, which is not representative of its true spatial position. Thus, the curvature of spacetime distorts our view of a distant object, creating images that change the apparent position of the background object to a new location. In this little cartoon, the object in the middle is the blue ball. Light emitted from this blue ball travels along the arrowed lines, always going in a straight line until they get to the observer's eye. Now, this path looks bent, but the spacetime is curved. Therefore, the straight lines in the curved space around the red thingy, which for us could be a black hole. Now, as observers, we look in a particular direction, say the top one. We see an image of the object in the direction that is above the red dot. The light rays are also bent to form a second image below the red dot. And it's really important to note that we do not see the blue ball in the middle. The light from the blue ball in the middle is sent on some other apparently curvy-wurvy straight path away from our observational location. We are then left only to see the two images above and below the red ball. It is in this sense that the trajectory of light's paths is changed from the straight lines of flat spacetime to the straight lines of curved spacetime. And this isn't just semantics or a trick or an illusion. Parallel transport in curved spacetime leads to fundamentally different results than in flat spacetime. The solid bent arrows are the true straight lines in curved space. They are not bent or deflected. The light is merely following the shortest path that parallel transports the tangent vector in the direction the light rays are pointed. As an important example that doesn't directly involve a black hole, but does involve curved spacetime, we reach back to April of 1990. 5 months after the launch of the Hubble Space Telescope, it captured 4 images of the same quasar in a gravitational lens, G2237 plus 0305. Called an Einstein cross, This image reveals a distant quasar gravitationally lensed 4 times by a relatively nearby galaxy. And as time went on, Hubble Space Telescope has observed a large number of these optical gravitational lenses. In 2002, astronauts on the Space Shuttle upgraded Hubble's imaging with the advanced camera for surveys. It had 5 times the previous sensitivity and observed some spectacular images of galaxy clusters gravitationally lensing some of the most distant objects we've ever seen. And one of them is this really fascinating and fortuitous observation of a background supernova being turned into an Einstein cross. The foreground galaxy cluster is about 5 billion light years away, and the distant supernova is about 9.3 billion light years away. The galaxy doing the lensing is the reddish blob, but the embedded distant galaxy is the bluish smear around it. The bluish smear is itself a strongly lensed background galaxy distorted by the path the light took on its way to our observational standpoint. On the right is the molten ring galaxy observed in 2021. This strongly distorted appearance is due again to the path the light traveled and not the galaxy's actual shape. The squishy appearance is also highly magnified. This magnification of about 20 times means that we see the faraway galaxy as larger, brighter, and distorted. Ophthalmologists and optometrists the world over would recognize such things as astigmatisms of the eye. But here, these astigmatisms aren't caused by a fluid or solid with some different refractive index than their surroundings, but rather due only to the shape of space-time itself. With respect to our black hole simulation from before, we see an Einstein ring. Here, the ring is formed from the background light of the Milky Way being directed toward us, which would have gone in a different direction had the black hole not been in that position. The black hole changes the shape of spacetime and thus alters from flat spacetime the path of the light. The symmetry in the ring is due to the extremely symmetric spacetime metric around a non-rotating black hole as envisioned by Carl Schwarzschild. Next, we see Dr. Hamilton's simulation of how Earth would appear to behave if it were orbiting a black hole with a mass of 2,000 times that of the Sun and at a distance of only 3 times the Schwarzschild radius. And one can imagine this is an extreme and absurd example, but it serves to show the important effects of curved spacetime. 3 Schwarzschild radii is the minimum stable circular orbit, and we are observing this event from not very far away at a distance of only 5 Schwarzschild radii. First, we see the obvious gravitational lensing, which makes it look like the Earth is being squished and squished. While the tidal forces would be huge and destructive to the Earth, let's assume an indestructible Earth just to keep things going. Then the effect we're seeing is the trajectory of light being reflected off the Earth from some bright ambient source. We can then actually see multiple images of the Earth as it orbits the black hole. Next, as Earth moves away from us on the right-hand side of the orbit, we observe a redshift. The relativistic Doppler effect is coming into play here, principally caused by time dilation for light arising out of the gravitational well. The time dilation also makes us measure time on Earth to run more slowly as it moves away from us on the right-hand side. The opposite blue shift and time contraction would occur on the approaching side. If this were really happening, the Earth would be orbiting the black hole at about 80 times a second, and that would be pretty bad. And we've slowed this down a lot. We've also slowed down what would be the tidal shearing between both sides of the Earth that would rip it to shreds. For one of the most realistic simulations of the conditions around a black hole, we can watch Christopher Nolan's movie Interstellar. He worked with the famous relativity researcher Kip Thorne to produce very realistic light ray paths. The odd ring and upward flow are due to the way light travels in strongly curved spacetime only, and don't reflect the physical shape of the accretion disk around Gargantua. It does lead to some artistic embellishments. The actual shape of this halo would be more squared off, as well as dimmed and reddened on the receding side and strongly brightened and bluer on the approaching side, just like the Earth thing we saw a moment ago. Nolan said that adding these bits of realism made the environment harder to understand visually, and Thorne, a good friend of his, understood and agreed. And besides, it's a film, not an explicit scientific treatise. As we saw earlier, a black hole with the mass of the Sun is only about 2 miles or 3 kilometers in diameter. The Earth, Moon, and Sun are really big compared to that. Also, a black hole is something that doesn't, by definition, emit light. So how do we see something that's really, really small and doesn't emit or reflect any light? And to actually find and witness a black hole and its effects would be amazing. To that end, astronomers have to look for the effects on their surroundings. A black hole in a binary star system may orbit close enough to its companion to draw material off the neighboring star and into a spiraling disk, like you see here. As the gas would spiral inward, friction would cause it to heat up to millions of Kelvin, hot enough to emit X-rays. Such companion stars would be seen to astrometrically wobble in the sky just like any other binary star system. But when something is too small to see, but is the mass of the Sun or greater, the spatially tiny object would turn its companion into what we call a single-line spectroscopic binary. We would observe the spectral lines from such a star to alternately blue shift and redshift in a regular way. Most of these are indirect measurements, as they don't directly measure the event horizon. Also, X-ray binaries could contain a neutron star rather than a black hole. However, there are two ways of directly measuring black holes that have only recently come into being. The first one is the measurement of gravitational waves, whose wave patterns, intensity, and frequency can only be created by mergers of ultra-compact, massive objects like some pairing of black holes or neutron stars. Last, and most recently, is the direct imaging of the shadow of an accretion disk around a supermassive black hole. The radio images, along with the polarimetry to show the ambient magnetic fields, conclusively show the existence of such objects close up. Let's review all three. The first place we can look for black holes is in binary star systems. Binary star systems make up a large proportion of stars in the sky, so we might expect to have some binary stars where one of the stars is very massive, goes through a catastrophic core collapse supernova, and forms a black hole. As a result of this evolution, its companion star will likely change its evolutionary path, becoming more massive due to the accumulation of material from the violent formation process of the black hole. As it does so, the secondary star evolves rapidly into a giant and fills its Roche lobe, which demarks the gravitational balance point between the star and the black hole. Matter crosses the balance point as the star expands in the throes of its red giant instabilities, dumping it into an accretion disk around the black hole. As this gas spirals in, friction causes it to get hotter and hotter into millions of Kelvin and hot enough to emit X-rays. The spectroscopy of the optical companion star is important here. The X-ray emission would tell us that some compact object lies there, but it is the observation of the spectrum of the visible star that can tell us the mass of the presumed black hole. The visible star is usually either a high-mass O star or Wolf-Rayet star, or it's a low-mass red giant or main sequence star. The spectral lines of the optical visible star will redshift and blue shift in a regular manner, which is interpreted as a Doppler shift as the star orbits its massive tiny companion. As of this video recording, there are about 4,000 X-ray binaries known to exist, but only about 220 of the optical counterpart stars have been cataloged in the AAVSO and GCVS standard community databases for variable stars. It is from this dataset of known X-ray binaries that we confirm the optical counterparts' properties. You'll see in the literature and poking around that there are roughly two types of X-ray binaries, high mass and low mass. This designation is not about the black hole, but rather about the star dumping stuff onto the black hole. When it's high mass, that's the O star or Wolf-Rayet. They're bright enough to actually measure the star spectra. But the low mass candidates are basically only detectable in X-rays. So for these, we frequently know very little about the donor star. The X-ray emission dominates the electromagnetic output from the pair in both cases. We looked at spectroscopic binaries back in my previous video on binary stars, but let's review it quickly here. In the case of high-mass X-ray binary, the optical star is an O star or Wolf-Rayet, and these types of stars are very bright, which means we can see a continuum spectrum. And these stars also commonly have emission lines and only a few absorption lines. So for this example, we'll focus on the emission lines. Let's say that the black hole in the binary is the black dot, and the yellowish dot is our hot, optically visible star. As these stars orbit their common center of mass, we see the emission lines redshifted and blue shifted compared to the laboratory reference frame. When the visible star is moving away, as in part 1, then we get a redshift. When it's moving towards the observer in its orbit, then we get a blue shift. This makes the determination of the black hole's mass easier. If we have a decent measure of masses from other O-type stars to apply here, then we can use this Doppler change to determine the orbital speed. Furthermore, from a detailed light curve, we can hopefully get the orbital parameters and the inclination of the orbit to the line of sight. This will then give us the masses of the two stars using Kepler's third law. If we have a good spectrum to mass relationship via a well-calibrated HR diagram, that gets us the mass of the O star and then the mass of the black hole. You can see there's a lot of measurements to go into this analysis. Next, what do we mean by filling the Roche lobe? This diagram shows the gravitational equipotentials of both the black hole on the left and the donor star on the right. There's also a line connecting their centers of mass, which would be their orbital plane seen edge on. Now, both objects have roughly circular rings of gravitational potential around them. This means an arrow from each ring points down towards the star at a right angle from the ring. Each arrow on a given ring represents the same pull of gravity, and the length of the arrow represents the strength of gravity's pull at that location, and the direction of the arrow always points towards the center of mass. If we move to an inner ring, the arrows would still point inward, but they would be longer to show the increased strength of gravity. If we go farther out, the arrows would still point towards the center of mass, but the arrows would be shorter to reflect the lessening pull of gravity at the greater distance. Now we look at the special crossing point between the two stars' gravitational potentials. This is the L1 Lagrange point, and it's where the gravitational force is completely balanced between the two stars. The green arrow points to this balanced spot, where if you just placed an object, it wouldn't fall either way. The figure 8 shape marked by the heavy white line and the red arrows is the maximum size the star can have before the material crosses the L1 point. The lobes of the figure 8 are called the star's Roche lobe. They mark the physically largest points where all the material of the star is fully bound only to one central star. We know that as stars evolve, they will grow in radius, not in mass, since being big here is a function of the gas's temperature and luminosity. The star here has swollen to nearly fill its Roche lobe, and we learned about this kind of evolution back in my videos on the future of the sun. Finally, the star has evolved to become physically large enough to fill its entire Roche lobe. The shape of the star is no longer spherical because the gravitational influence of the nearby companion black hole has changed the gravitational equipotential of the entire system. If the star gets any bigger, which it presumably will, then some of the star will cross into the black hole's Roche lobe limit and fall towards it. The star would then become so big that its outermost layers are not held onto it alone. They are held instead inside the peanut-shaped outer gravitational equipotential lines. This simulation shows the effect of this late-type giant star overfilling its Roche lobe. Some material crosses the L1 point, which is the natural dumping point through which all the material would likely squirt. The simulation also adds in the effects of their orbit, and since they orbit a common center of mass, or barycenter, we see that the black hole must be much more massive than the star, because the black hole isn't moving as much as the big star. The angular momentum of the gas from the star is retained as it falls across the Lagrange point, creating what's called an accretion disk around the black hole. And that gas gets to millions of Kelvin in temperature as it spirals in, emitting the X-rays that we observe. In this simulation by NASA's Scientific Visualization Studio, we see the motion of the X-ray binary XTE J1550-564, otherwise known as V3081 Norma. The binary star system is composed of a black hole around 10 times the mass of the Sun, and the star in this case is a K3 giant. Additionally, not shown in this simulation, the black hole fires out jets of matter along a strong magnetic field created by the inner accretion disk, and it's also known as a microquasar. These X-ray binaries all emit a majority of the radiation in the X-ray part of the spectrum. The X-ray emission is generally thought to be the result of accretion of matter from the normal star onto the compact object. If such a system emits signals that can be directly traced to the compact object, then it can't be a black hole, but rather it'll be a neutron star. However, we can lock in the black hole nature of such stellar mass black holes by the spectroscopic analysis I just described. By studying the companion star, we get the orbital parameters of the system and obtain an estimate for the mass of the compact object. If this mass is much larger than the Tolman-Oppenheimer-Volkoff limit, this is the maximum mass a star can have without collapsing, then the object can't be a neutron star. That leaves us with our black hole as our only current option. Quark stars and their ilk are still in their infancy of understanding, therefore the black hole paradigm for the massive compact object is the current understanding. The Tolman-Oppenheimer-Volkoff limit is currently known to be between about 2 and 2.2 solar masses. But for most astronomers, the ambiguity is removed if the compact object is above 3 solar masses. A 3 solar mass neutron star just can't exist in nature. Though we have good confirmations of only a few dozen solar mass black holes with mass ranges between about 4 and 20 solar masses, it's thought that there should be about 1 billion such stellar mass black holes in our Milky Way. This number comes from the expected initial mass function of stellar evolution for the composition and population of known Milky Way stars. These black holes would have been formed from titanic supernova events. Since black holes are quite small and don't emit light, they reveal themselves only by interacting with a star or gas nearby. Now let's take a look at some known candidates. Let's now discuss the observational evidence for black holes. We'll start with the one that is usually described in detail to all introductory astrophysics students, Cygnus X-1. Located in the constellation Cygnus near the bright star Eta Cygni, at a visual magnitude of 9, it can be actually picked out with a backyard telescope. These images from the Space Telescope Science Institute's DSS-2 photographic survey show its position and relative brightness to Eta Cygni. Zooming in, we see an artist's impression of this fiducial X-ray binary. Discovered in 1964, Cygnus X-1 is consistently the brightest source of high-energy X-rays in the sky. We see here its appearance in X-rays from the Chandra X-ray Observatory. The angular size of the image is about 1.5 arc minutes, or about the same angular diameter as a big crater on the Moon. The spectrum on the right shows a Doppler-broadened ionized iron emission line from close to the black hole. Initial astrometric measurements from 1972 to 1974 led it to be the first astronomical object widely accepted to be a black hole. Since then, it has been studied extensively due to its proximity and brightness. The optical counterpart is a late-type O9 supergiant with a mass estimated between somewhere 20 and 40 solar masses. Based on stellar evolution models that utilize its observed spectrum, as well as VLBA and Gaia astrometric measurements, Cygnus X-1 is estimated now to be approximately 2,220 parsecs distance. With this distance, and using a light curve that shows a 5.6-day non-eclipsing period, it was found to have a nearly circular orbit of 0.2 astronomical units, approximately half the distance between the Sun and Mercury. Since an O-type supergiant would be about 15 or so times the size of the Sun, this star reaches about halfway to the black hole. The star is about 0.1 AU in size, or 1/10 the size of the Earth-Sun distance. Supergiant stars really are big. Now, this star isn't expected to be currently overfilling its Roche lobe, so the artistic impression here is due to the massive stellar winds that are present in stars like these. But the effect is the same. Material dumps off the star and creates an accretion disk around the black hole. We know it must be a black hole because numerous measurements put the compact object's mass somewhere between 14 and 21 solar masses. There is some tension, but the higher mass estimate uses the astrometry from the VLBA and Gaia to pin the distance very tightly. The higher measurement seems to be the current consensus for the mass of the black hole. No matter what, both of these are much larger than the Tolman-Oppenheimer-Volkoff limit of about 2.2 solar masses. The accretion disk of Cygnus X-1 is known to be relatively small due to the rapidity of the X-ray bursts. For example, if an X-ray burst occurs within a millisecond, this implies that the region emitting the burst can't be larger than 300 kilometers across. Thus, the event horizon must be smaller than this size, marking 300 kilometers as the upper limit for it. We know from before that the event horizon for a 15 solar mass black hole will be about 45 kilometers, so the X-ray bursts are coming from the innermost ring of the accretion disk. So this artist impression is really wrong, isn't it? The black hole's shadow could not be seen against the incredibly bright disk, and the disk would be approximately 15,000 kilometers in size, or about 300 times larger than the black hole. Also, the disk is only 15,000 kilometers in size, and that's nothing compared to the 30 million kilometer diameter star. So the star is 2,000 times bigger than the disk, and the disk is 300 times bigger than the hole. So yeah, the artwork is really not to scale. As for where the black hole came from, assuming a 15 solar mass black hole, the star that formed it must have had a mass greater than 40 solar masses. We can also deduce this because the binary pair seems to be part of the Cygnus OB3 stellar association, and the largest known star in that group is 40 solar masses. This black hole must have formed from a bigger star that evolved much more quickly than the current most massive star. Come on, what's up? Such a huge star could have ended its life as a collapsar. It might have never made a supernova and just collapsed directly down to a black hole without exploding. Prior to this destructive event, the star would have been shedding mass rapidly as a Wolf-Rayet star. Its companion O-star would have accumulated some of that star's stellar wind. And indeed, it does have elevated helium compared to other O-stars, so the scenario of a massive Wolf-Rayet star collapsar is a likely model. Cygnus X-1 is typically held up as a prime example of stellar mass black holes. There really are not a huge number that are known, only a few dozen known or candidate black holes of this mass range. So you'll likely hear about Cygnus X-1 from many places as you look into high-energy astrophysics. Now let's look at the other methods of detection. Our Milky Way is our home galaxy, and at the center of it, in a truly dark night sky, can be amazing. This image shows the wonder of what you can actually see far away from city lights. The center of the Milky Way features prominently in this image as a home to vast quantities of gas and dust and a concentration of older stars. The gas and dust obscure our view of the center of the Milky Way, so we need to observe in wavelengths of light that are unaffected by its presence. X-ray light can penetrate this veil. This 400 by 900 light-year mosaic of several Chandra images of the central region of our Milky Way galaxy reveals hundreds of white dwarf stars, neutron stars, and black holes bathed in an incandescent fog of multi-million degree gas. The colors indicate X-ray energy bands. Red is low, green is medium, and blue is high-energy X-rays. This image is the result of 94 hours of continuous observation by the satellite. The dead center of the Milky Way is located inside the bright white patch in the center of this image. It's relatively nearby at 26,000 light-years away. Radio wavelengths of light are also unaffected by gas and dust. This VLA image at 90 centimeter wavelength shows the inner 240 light-years of the galactic core. It's quite a tangle of activity, with numerous supernova remnants and the effect of large-scale magnetic fields, jets, and high-speed gas flow. Each inset zooms in with a different wavelength of radio light until we're looking at the inner 2 by 2 light-year square in infrared wavelengths. To take that image, a group led by Andrea Getz at UCLA used the Keck Observatory's infrared cameras on top of Hawaii's Mauna Kea to image the central region. The Earth's atmosphere adds a lot of turbulence, so the researchers use an artificial laser-created fake star in conjunction with adaptive optics in the observatory's cameras to remove the effects of the lightly churning air above. The result of their work is this image of the inner 2 light-year by 2 light-year region of the center of the Milky Way. We see the extreme density of stars in that region. For comparison, the Sun's nearest neighbor is over 3 light-years away, so our local solar neighborhood would only have 2 stars in an image of the same volume. The geometric center of the Milky Way, which is the center of the X-ray and radio images you saw before, is pointed out with the arrow. The image to the right shows only the inner light month across. It reveals the true goal of Getz's 20 years of work. which was to map the orbits of stars in this inner region. All of these stars are moving extraordinarily fast, and according to Kepler's laws, must be orbiting something extremely massive. The pinnacle of this work was to observe a full orbit of their innermost star, S2, over the course of 16 years. This observation series conclusively showed that the star is orbiting something that is 4.3 million solar masses. This is the sign of a supermassive black hole. In all the previous images, we only saw stars and gas and dust, but something with that mass that doesn't emit light at any frequency must certainly be a black hole. In May of 2018, this star came within 100 astronomical units of the central object that it is orbiting. Now, a black hole with 4.3 million solar masses would have an event horizon size of about 0.1 AU. So the star passed within about 1,000 times the black hole's event horizon. During this pericenter passage, the difference between S2's orbit as described by both Newtonian and Einsteinian gravity was significantly larger than the measurement uncertainty. This meant that they could tell the difference between Einstein's theory of general relativity and Newtonian mechanics in this observation series. The result was that spacetime was shown to be curved as Einstein said it would be and Schwarzschild discovered back on that battlefield in 1915. The difference comes in the observation of the actual orbital curve as well as the speed of the star itself. During previous para-black-holian in 2002, it was traveling a few thousand kilometers per second during its closest passage in its orbit. This is all very convincing dynamical evidence for the existence of a supermassive black hole. Next, we move on to some extremely convincing evidence for the existence of stellar mass black holes. With the first ever observation in September of 2015 of a truly convincing gravitational wave signal from the LIGO group, the next major step was to understand exactly what created the observed waveform of the signal and ensure it wasn't noise or a fluke. Visually, the signal at the two detectors was unambiguous and identical. One of the most important elements of the LIGO collaboration was the creation of a huge database of simulated signals. Many types of inputs, from neutron star quakes to colliding white dwarfs to neutron stars to merging black holes, were calculated for a myriad of masses and orbits. The two top plots show the data received at Livingston and Hanford, along with the predicted shapes of the waveform. These predicted waveforms show what two merging black holes should look like according to the equations of Albert Einstein's general theory of relativity, along with the instrument's ever-present noise. Time is plotted on the x-axis and strain on the y-axis. Strain represents the fractional amount by which the distances of the interferometer were distorted, which was actually smaller than the width of a hydrogen atom's nucleus. As the plots reveal, the LIGO data very closely match Einstein's predictions. The plots also compare data from both detectors. The near absolute match of the two plots demonstrates that both detectors witnessed the same event, which confirms the veracity of the detection. Based on the observed signals, LIGO scientists estimated that the black holes for this event were about 29 and 36 times the mass of the Sun, and that the event took place 1.3 billion years ago. About 3 times the mass of the Sun was converted into gravitational waves in a fraction of a second, with a peak power output of about 50 times that of the entire visible universe. What we see here is a simulation of that merger. The background stars appear warped due to the incredibly strong gravity of the black holes. The black holes warp space and time, and this causes light from the stars to curve around the black holes. The ring around the black holes after they merge is known as an Einstein ring, arising from the light of all the stars in a small region behind the holes, where gravitational lensing has smeared their images into a ring. There wasn't an optical counterpart that was observed with this merger, so what we see here is strictly a simulation. The actual observation was the signal shown by the graph previously. This detection probes the spacetime right up to the event horizons of the two black holes. So this observation, along with hundreds of confirmed mergers like these since this first one, is some of the best evidence that we have for the existence of black holes. But in this day and age, there are a lot of people whose mantra is "pics or it didn't happen." All the gravitational wave events are real signals in the distortion of spacetime, but they are not pictures. So are there images of black holes? Yes. We can look for black holes where their effects are evident. Many galaxies are what are known as active galaxies. These galaxies have cores whose luminosities exceed the rest of the disk or halo. They also may have jets that extend to millions of light years for the most energetic of variety. Looking specifically at the galaxy M87 in the constellation Virgo, about 53 million light years away, we see the supergiant elliptical galaxy with a bright core and a visible jet extending about 5,000 light years. This jet has a distinct structure that can be seen in radio and visible light. At the highest magnifications in the radio wavelengths with the VLBA, knots in the jets can be observed to change year to year on size scales of about 1/10 of a light year. The material in the jet is traveling at about 85% the speed of light, and the energy contained in the jet is about 10 to the 13th times that of the luminosity of all the stars in the Milky Way. The astounding energy that propels this jet is coming from a volume that cannot be bigger than a few light years across. Again, in the Milky Way, the typical distance between stars is about 3 light years. So how is something creating 10 to the 23rd solar luminosities in a volume smaller than the distance between the Sun and Alpha Centauri? The answer is a supermassive black hole. The Event Horizon Telescope collaboration was formed to image that black hole. M87 is near enough and is near the ecliptic, so a worldwide observation campaign to use radio telescopes in the submillimeter microwave region of the electromagnetic spectrum was used. Each was outfitted with an extraordinarily accurate clock, and all observed the galaxy at roughly the same time. The signals could then be combined interferometrically into a telescope with the size of the Earth. The huge amount of data was stored on hard drives, and because of the distance between the telescopes, transferring the data to a central processing location would literally take years using internet connectivity. The collaborators then packed the drives into suitcases as carry-ons on airplanes and flew copies to Germany and Massachusetts for processing. On April 10 of 2019, the Event Horizon Telescope collaboration announced the first ever direct image of a black hole. This is the central region of M87, spanning only 13 thousandths of a light year across. What we're looking at here is the image of the rotating disk of ionized gas with a maximum diameter of about 25,000 astronomical units, well outside the field of this view. Here we only see the brightest regions of the black hole. The size of the inner shadow of the black hole is about 4 times the width of Pluto's orbit around the Sun. And if the Sun were at the center of this image, the Voyager 1 probe would be just going to the glowing region at the dark center. The Event Horizon Telescope group was able to measure the black hole's mass at 6.5 billion solar masses. This would have a Schwarzschild radius of about 120 AU. The shadow you see in the center is about 500 astronomical units across, so the hole itself is about 2.5 times smaller than the shadow that it casts. The reason for this difference in brightness is the gravitational lensing we talked about earlier. In 2023, the EHT data were reconstructed with an improved interferometric algorithm, PRIMO, to enhance the resolution of the image. Again, the shadow of the black hole is about 2.5 times bigger than the actual hole itself, and closely resembles the images that Kip Thorne and his collaborators did for the movie Interstellar. But that was Hollywood, and this is reality. The Event Horizon Telescope group subsequently also imaged Sagittarius A star in the center of the Milky Way. In both cases, we see the expected glowing accretion disk around the black hole gravitationally lensing the light around it. We also see the size difference between these two behemoths. Our home galaxy's supermassive black hole is 1,000 times smaller than the epically large black hole at the center of M87. This accretion disk and the intense magnetic field generated by infalling matter are understood to be the source of the relativistic jets emanating from M87's core. We've only really described the evidence for the existence of stellar mass and supermassive black holes. Stellar mass black holes are found by looking for their X-ray binary signature or by their gravitational wave signals as they merge with another compact object. Supermassive black holes, on the other hand, are found at the centers of nearly every galaxy and usually have masses of at least 1 million solar masses. But there should be something in between. Right now, though, the intermediate mass black holes with sizes between a few hundred solar masses and 1 million times the mass of the Sun are scant and only in the beginning stages of discovery. Understanding the growth and evolution of black holes up to supermassive sized ones is an active area of research, and searches for these middle mass black holes are underway. What is the ultimate fate of a black hole? Do they change? Well, yes. They accrete mass upon themselves and get bigger. But how can a black hole die? To do so, black holes wouldn't actually be completely black. According to classical general relativity, they are completely dark with nothing, not even light, ever able to escape. But this perspective doesn't take into account quantum mechanics, which introduces some intriguing ideas. Stephen Hawking proposed that in an intense gravitational field surrounding a black hole, the gravity is so powerful that it can generate subatomic particles and light. As these particles are created, one particle could fall into the black hole while its antiparticle escapes. This extremely rare process would lead to the gradual emission of particles. This tiny outbound trickle, which could be classified as thermal radiation, given that it corresponds to a specific temperature based on the size of the black hole, could cause the black hole to effectively lose mass. The luminosity of this particle emission would be proportional to the inverse of the black hole's mass squared. The bigger the hole, the less the emission. Since it would be a particle emission, we could characterize it with an effective temperature. To that end, smaller black holes would have a higher temperature, resulting in faster rates of evaporation. For example, a solar mass black hole would take approximately 10 to the 64th years to fully evaporate, whereas the estimated age of the universe is about 10 to the 10th years. This means it would take about 10 to the 54th times longer than the current age of the universe for a single solar mass black hole to evaporate completely. And for a supermassive black hole like M87's to evaporate, it would take on the order of 10 to the 102nd years. Hawking radiation is obviously a fascinating concept, but it does not have any significant implications for today. There's so much more to learn about black holes, but I'll leave that for other videos. Watch my videos about quasars and about the Milky Way to learn about the black holes that power their cores. Also watch my videos on gamma ray bursts and the amazing discoveries by the LIGO and EHT collaborations. Since you made it all the way to the end here, you should subscribe to my channel and give it some likes. Also, please consider becoming a channel member or joining my Patreon group. This support goes a long way to helping me produce these kind of long format videos. Thanks for watching, and we'll see you next time.